Let's have a look at power in an LCR circuit. Now, I know you've already done this with your level 3 class, but I thought we'd just go over a few little issues here. Let's draw our phasor diagram. I'm going to put one there, and one there. Now, we know that this represents a phasors. This little object is rotating in that direction, so it's got a rotational speed. We'll call it omega if we like. We know that at any point in time we can stop this rotation, and we can project onto a screen over here the vertical components, and that will be the value at that point in time. So some of the time these phasors will be 0, some of the time maximum positive, some of the time maximum negative. Right now this one's maximum positive, and this one's maximum negative, and this one is 0. This one, VR, the voltage across the resistor. Remember, this is a circuit like this where we've got an AC power source, we've got a capacitor, we've got a resistor, and we've got a coil. So we've got all three there. Now, which one is the bottom one? We know we've got a voltage there, and we know we've got a voltage there. Which one is which? Well, when we're looking at a capacitor being charged, the top one there, we know that its curves are like this for charging. And we know that that one's the VT graph and this one's the IT graph. So from that graph there we can work out which one gets its voltage first. Now, I didn't talk about current on this little diagram, but the current is always in phase with the resistance. So we'll make our current there. Our current's a little green one. So current is in phase with the voltage across the resistor, and the current's the one thing you can rely on in these circuits. So looking at this one over here, the capacitor diagrams, voltage is 0 and takes time to build up. Current is at its maximum earlier than the voltage is at its maximum. So if current is at its maximum earlier, if we rotate that round 90 degrees, the current will be at its maximum and the voltage across this bottom one will be at its minimum. So this must be a capacitor. Alright, now if we were to look at the inductor curves, so that was the capacitor curves, this is the inductor curves, then on this one it's the current that takes time to build up with the inductor. The voltage across the inductor is maximum right at the start. It's a voltage curve for the inductor. So we know that the voltage on the inductor is high before the current. So this must be the inductor. So this top one's the inductor, the bottom one's the capacitor, the voltage across the resistor is the middle one. Now, if we want to work out the voltage of the supply, then we must subtract the voltage of the big one, the little voltage here from the big voltage here, because the voltage across the inductor and capacitor are totally out of phase, 180 degrees out of phase. What does that mean? That means over here on this diagram, if that one was a positive, then this one will have a voltage. Now, we've said that the voltage across the capacitor here is about that big. That means the voltage across the inductor is a bit bigger, and its polarity is round the other way. So that means it would have a negative at that end and a positive at that end, right? So polarity is round the wrong way, they cancel out a little bit. So we subtract the little one off the big one. That would leave only a small little voltage on the inductor side. So this circuit is primarily an inductive type of circuit because the inductance is bigger. We then would have, so let me just, if we subtract those two vectors, we're left with a small vector at the top, we're left with the resistance as it was, and we're left with a VS. So our VS looks like that. So when we actually are working out the VS, we can say VS is equal to VL minus VC squared plus VR squared all over the square root. Right? That's just Pythagoras. There is a phase angle, and the phase angle is between VS and VR. Now when you're looking at power in a circuit, right, we're looking at power, so let me just draw this in a little bit more detail. We've got Vs like this, VR, that's our phase angle, Vs times the cos of theta equals VR. Right, you can see that. Now, power in these circuits is only expended in the resistor. So we all know that power equals VI, but which V? We don't use the V on the inductor, we don't use the V on the capacitor, we don't use Vs. We just use voltage on the resistor because that's the only component that's actually expending power as heat and losing power. Now the energy in the inductor, and there is energy in the inductor, and we're going to show another little video the way this all works, and there is energy in the capacitor at different times. Alright, now the energy in the capacitor is at its most when the voltage is at its most, and the energy in the inductor is at its most when the current's at its most. So we'll look at that, like I said. But the voltage in the resistor, okay, times the current will be the power being used. So that's Vs cos theta equals VR times the current. So if we say that power equals that, we've got to ask ourselves, are we talking about RMS power or peak power? So if I use VRMS, IRMS, then I've got power RMS. Okay. There is a peak power though, and that peak power is when we're looking at the peak value for the voltage and peak value for the current. So having said that, that's our power situation. Let's just look at a few of the other things. How did we work out I? Well, we work out I by Vs divided by Z equals I. Right. Now again, how is that? Is that an RMS I or is that a peak I? Because I goes round and sometimes it's 0, like right now it's 0, sometimes it's maximum positive and then maximum negative. So Z is your impedance. Z equals XC minus XL squared plus R squared. We'll take the square root. That's our Z. This is constant. Z does not change. Alright. Vs doesn't change. Not the length of the vector. But it does change when it's positive, when it's negative, when it's 0. Alright. So we can get a Vs which is an RMS or a Vs which is a peak. Again, if we use Vs as a peak, we'll get I as a peak. If we use Vs as a RMS value, we'll get I as an RMS value. So there's two types of power, peak power and RMS power. If we use I as VMS, so we could say power equals V RMS if you like, just put an R, times I, which is Vs RMS, all over Z. So V squared over Z, which we're well used to. So that's power in an LCR circuit.